Hi, and this is section 3. Last but not least, which is the composition of transformations. So first we talk about introduction of matrix, how we can multiply a matrix to a vector, right? And how do we do stuff with matrix? Right, then we describe how does the matrix multiplication becomes a transformation. And we focus on rotation because that's where we use a lot, and we have rotation in terms of a matrix. Yeah, this kind of matrix with the angles cosine and sine multiplied by a vector. So that's a rotation. And something else, but we don't use that too much, so we kind of like skim that. And lastly, we're going to talk about composition of transformations. But first, let's recall what is a composition, because we mentioned that last time. If you remember, whenever you have we do things in a sequence. For instance, you can have a ball. You can paint it to be green, and you can increase the size to be twice as large. Right then, those two operations, once you do it one after another, is the composition. You compose things, you add these two things together and make it as though we perform a single operation or a single transformation. And it form in terms of matrix. Oh, and back then when we talk about composition for one dimension, that was easy, right? Because if you have, let's say the first transformation, say you add 1 to a number, like you move everything to the right by 1 point. And the second transformation says you multiply everything by 2. Once you compose them, you do these two transformations in order. By definition, we do the inner one first. So we do the one that is close to the number first. So in this case, you multiply everything by 2 first, and then after that you move everything by 1 point. So this was the transformation in one dimension, where all you have are functions, and you can compose functions by using the definition of a function. So that's a composition in one dimension. And the simple thing about that transformation is that there are only 2 basic operations you can make. You can add or subtract by a single number, by a single constant, or you can multiply a number by a factor. And based on only these 2 numbers, and all the possible transformation you can make is always in terms of a times x plus b. At the end of the day, then the result is always in this form: a times x plus b. And here likewise, right, we move on from 1 dimension to 2 dimension, right? And we can still compose things, because if you can express, or if you can explain them verbally, then of course we can explain the same concept using matrix. Right, for instance, if you think about it this way, suppose we start with this square. Suppose in the first step we increase the size by 2. So in this case we start from dilation. Then we have a square that is 2 times that large. And then what if we rotate that by, let's say, 45 degrees counterclockwise? Then the result would be something like that. So you scale and then rotate, and here we get the result of this composition of these 2 transformations. And just do it one after another, and we get a new one. And the nice thing about doing it using a matrix is that whatever kind of transformation, as long as it is linear, as long as you can represent them as a matrix multiplication, right? Then any kind of composition can be combined, and the result would be just a new matrix. It is as if you simply multiply the result by a single matrix. Just like what we have here. You may have multiple numbers. Like maybe for instance you may have 2x plus 1 as one of the transformation. Then we have 3x plus 4. But at the end of the day, if you do the math correctly, then we can somehow combine them and make, let's say, 6x plus 7, for instance. Any kind of linear transformation can be composed into just a new linear transformation. I'm just gonna skip the math here, but that's a result looks similar to what we have at first. Similarly, what we are doing here is if you can explain each transformation using a matrix, maybe let's say this is the first matrix, A1, B1, C1, D1, and there's a second matrix, A2, B2, C2, D2. Then the result of everything after we perform these two operations is a new matrix. Let's say A3, B3, C3, D3. Where there is some kind of magic behind that. There's some way where we can combine these two matrices together to produce the third matrix. As if we just, perform a single operation or a single multiplication. Which is pretty handy, right? And because now, we can just study the basic or the base transformations. And if you want the fancy transformation, then you can produce that by, just by chaining or doing these transformations one at a time. And then multiply everything together to get just a single matrix out at the end. And that would be easy to, to compute. And it is exactly what the motivation for the matrix multiplication is. If there is a way to, to combine these two matrices together to produce a new transformation, then that means the way you multiply or the way you combine these two matrices to compose these two matrices, I should follow some kind of rule. For instance, here we have if we multiply two numbers together, you get a new number. This is the simplest one, the simplest case in one dimension. And likewise, if you have two matrices together, and then you multiply that to a vector, let's say v1 and v2, then the result should be we wish at first. We wish that we can combine them somehow to produce a single matrix as a result. And of course, there's a way to accomplish that. Oops. Okay, let me take a look at my cheat sheet. There's a link to this nice animation from 3 Blue 1 Brown. And let me put a link in. Takes a while to load. It started at 4:29. Let's take a look at that for a moment.
Let's look at another example. Take the matrix with columns 1, 1 and -2, 0, whose transformation looks like this. And let's call it M1. Next, take the matrix with columns 0, 1 and 2, 0, whose transformation looks like this. And let's call that guy M2. The total effect of applying M1 then M2 gives us a new transformation. So let's find its matrix. But this time, let's see if we can do it without watching the animations, and instead just using the numerical entries in each matrix. First, we need to figure out where I hat goes. After applying M1, the new coordinates of I hat, by definition, are given by that first column of M1, namely 1, 1. To see what happens after applying M2, multiply the matrix for M2 by that vector, 1, 1. Working it out the way that I described last video, you'll get the vector 2, 1. this will be the first column of the composition matrix. Likewise, to follow j hat, the second column of M1 tells us that it first lands on -2, 0. Then, when we apply M2 to that vector, you can work out the matrix vector product to get 0, -2, which becomes the second column of our composition matrix. Let me talk through that same process again, but this time.
So that's the concept of the multiplication. And so you combine the two transformations together, and then this. Actually, I suggest you watch the whole clip if you have time. But in the sense that, okay, if you define matrix multiplication as a composition, then it kind of makes sense that it should be defined this way. So that was the motivation, right? At first, we haven't talked about how we multiply this in the first place, but we're gonna see in a moment that it should make sense if you do it this way. And we start from the first composition. In this case, it transforms these two vectors to these two new vectors, and then we transform this result to a new vector. And so it's as if you transform the original vector to this new vector, and then the original j vector to this new vector. And so that's the result we want. But the question is, if you want to do it numerically, if you want a formula, given any 2x2 matrix, is there a formula that will help you multiply out these vectors? And the answer is, of course, yes, there is a way to multiply them out. And let's start from the bad way to multiply. Not the bad way, but that's I believe this is the way everyone has been taught, which is to remember this formula. Let me zoom in a little bit. Let's take a look at this haunting formula. We just passed Halloween in a week, but we get haunted. So we have A1, A, B, C, D, and then A prime, B prime, C prime, D prime. And the way you multiply matrix data is we get this result. It's again not friendly, right? But you can see the way I highlight the colors to make it slightly easier to see where things go. So the first matrix, the one on the left, right? We take the rows, we divide it into two rows, but the one on the right, we divide it into two columns, not rows. And the way we accomplish this is we multiply the first row to the first column. So A to A prime and B to C prime. That's the formula for the first one. And then for this entry, like the first row, the second column, we multiply, of course, the first row of the first matrix to the second row of the second to the second column of the second matrix. So it's A times B prime and then B times D prime. So that's the second one. Third, we have CD, which is the second row, and we multiply that to the first column. So it's C times A prime and then D times C prime. And lastly, we have what remains, which is the second row of the first matrix. We multiply that to the second column of the second matrix, which is C times B prime and D times D prime. So in a sense, we have the first row on the first row, like the second row stays on the second row, and also the first column stays in the first column, the second column stays in the second column. But we kind of like crisscross, right, from one vector to another. So that's the result, which kind of looks confusing at first, and of course it's still confusing even if you do it like 5 times, 10 times already, right? But this is the definition. If you want a single formula that you can apply, then here is a formula. Right? But if you want to, to dissect, to at least, do it step by step. Like the way things work and the way it is defined as follow. Okay, so you again split them into columns, just like what we did earlier. Like we think of a matrix as two vectors where each column represents a single vector. And here, another way to look at the computation is that the left part, right, the first vector of the result is the matrix multiplied by the first vector. So we split the pie into two matrix vector multiplication. Then the left part of the result is the first matrix and the first column of the second vector. And the right half of the result is still the first matrix, but multiplied to the second column. So in a sense, what we are doing here, right, is we think of it as just a single matrix. Let's call it A. We multiply A by the first vector, and then we multiply A by the second vector. And here is the result that we are left with. That's A. That's the whole matrix to the first vector, and that's the first half of the result. And then we multiply A to the second column, we get the second half of this result. So now we kind of like have two smaller tasks to perform. And also the nice thing about this is this actually describe what is going on behind the scene, which we will see in a moment. But for now, let's see if we can multiply matrix in this way. So that's the formula. Oh, and you can use either method. You can do everything at once if you want to, or you can split them into two tasks. Up to you. Like for instance, and this is an example where you do everything at once. So if you are given these two matrices, you are asked to multiply them together, and here's the result. So we have the first row of the first matrix here and there, and then that's the first column of the second matrix is there. So you multiply 1, 2, 2, 0 minus 1. Like 1, 2, 2, 1, 2, 2, 0 minus 2. 1, 2, 2, 0 minus 2. And the result is 4. That's the result of multiplying the first row to the first column. And that's 4. And then we repeat that to other entries. And for instance, let's clear that out. And for this entry, the top left, you get that from multiplying the first column of the first matrix to the second column of the second matrix. And you get 1, 2, then 1. Oh, sorry, that's a typo. That should be 3. 1, 2, and 1, 3. And the result should be... I didn't see that last time. The result should be 7. 1 times 1 is 1, 2 times 3 is 6, 1 plus 6 is 7. And that's the top right entry. And just repeat that for the rest of the matrix. Oh yeah, there are 2 typos here. It's second row to the first column. So you get 3 times 0 and 4 times minus 2. The result is 8. And finally, we have 3, 4 multiplied by 1, 3. So it's 3 times 1, which is here, and then 4 times 3, which is here. And the result, after we add the result together, we get 15. So that's the answer for the matrix multiplication. And so that's that's a single formula if you want to do everything at once. But what I kind of recommend, and also what makes sense in terms of transformation is you split this task into two multiplication. Like the first one here, where you multiply the matrix on the left by the first column. And here, if you remember the formula we have back then we have this formula when you multiply the matrix in this way. So 0 to the first column and then -2 to the second column, which gives you 0, 3 and -4, -8. So that gives you -4 and -8. Oh, sorry, 0, 0, not 0, 3. So it's gone. And the result here, as you can see, is the first column of the resulting matrix. So we are correct. And for the second column of the result, then we repeat the same thing but with this new vector instead. So we have 1 and 3. Split them in this way. And this one is multiplied to the first column, which is 1, 3. This 3 is multiplied to the second column, which is 2, 4. Result is 1, 3 plus 6, 12. It is 7, 15. And of course, as you can see, 7, 15 match the second column of the result. So this is one way you split the task into two smaller tasks, and so that you can compute each of the column separately. But again, this is method 1. This is method 2. Use your favorite method. Okay, so that's the way you multiply matrix together. You can practice multiplying matrix together 10 times. But again, the important part is not the result, because again in practice you can use formulas, you can use tools to help you perform that task. For instance, if you go back to that Desmos website, actually you can multiply. They also have a matrix calculator. Let me go there first. We'll give you the link in a moment. So if you go to Math Tools and select Matrix Calculator here, then you're gonna get a matrix calculator. The way this works is you just add entries. Okay, new matrix. That's an A. So what do we need? 1, 2, and 3, 4. Okay, 1, 2, 3, 4. Done. Okay, what's next? 0, 1, -2, 3. 0, 1, -2, and 3. Done. That's the input. Then, what do we need? We don't need a new matrix. We need a new line, which is A times B. And bam, we get the result right away on the right. Oh, you can see it on the screen, my bad. But yeah, that's the result of the multiplication, which is nice. And of course, in practice, you not just use any of your favorite tool you have. And what is more important is the result or the meaning behind this multiplication, of why we have to do it this way. And so that's the tool, and also a reason why I didn't have that as an exercise, because it's about using tools. It's not about doing math. And the important part and the more fun part is the next part, which is about decomposition. So at first we claim, right, we didn't prove, but we claim that if you want to compose two transformations and combine them into a single transformation, then we can achieve that by multiplying two matrices together, get a result. And the way we multiply that to make this work, we have to multiply it using this formula, or multiply it in this way. Right, and let's see how that works in practice. So we didn't have that, but I'm gonna add it. So let A and B be matrices. Then A and B, they might or they might not. Like they might describe some kind of transformation. Like for instance, in this example, like we have a shear. Let's say that's an A, and then the rotation, that's a B. Like we first rotate a vector, and after the rotation, then we shear it. We change it. So this is the composition of the transformation. And we can write it as using the composition symbol. Right? But since they are matrix, then we don't need this thing anymore. We can think of it as a matrix multiplication. So on the left, we have two different transformations. On the right, this new matrix is A times B. If you perform the multiplication as we just described above, then this A times this B gives you this new matrix. And this new matrix is the composition of these two transformations. So instead of performing two tasks, like one at a time, we can do them both together at once. And this new matrix, once you multiply to the vector, we give you a new vector that will tell you what the new transformation or what the new vector looks like. And so that's the reason behind learning the matrix multiplication, which is to understand and to condense, like to combine two transformations together and get a new one. So at this point, right, you can see, okay, you can rotate and then shear and then get a new transformation, get a new composition that we don't know about. And what is the application? You ask, and yeah, I don't have it here, but let me give you an example of some of the application of this sequence of operations. For instance, there's an example here. Suppose there are two transformations. Right, the first is the dilation, like by a factor of 3. So that's the first one. Let's say it's an A, and let's say we knew that if you scale everything by a factor of 3, and that's the same thing as multiply the whole thing by this matrix. And then suppose we have another one, which is the dilation by a factor of 2 instead. Factor of 2. Let's say that's a B, and again we can describe that transformation as this matrix. Then the question is, what is A times B? Right, and we can describe that A times B. We can describe that product in two ways. First, we can describe it using, let's say, like verbal, or using your imagination verbally. In this case, we can describe, if we understand what is going on, right, by this transformation, then we can combine them. And second, we can describe by using a matrix, which is what we did recently. So let's see what are these two. So let's start from verbal transformation, right? Because think about it. If you increase the size of something by a factor of 3, and then increase the size again by a factor of 2, what would the result be? If you imagine doing these two in order, if you have a box, you increase the size by, you make it 3 times larger. If you have a box of 1 by 1, if it's 3 times larger, then you have a box that has length 3, right? And if you do it again, but now you increase the size by 2, what would be the result? It's a box that is 6 times as large. Simple, right? And yeah, that's what we mean by described by the verbal transformation. And this doesn't require too much math. Like it does require some kind of basic vocab, like the relation, reflection, rotation, and use some of your imagination to see if you perform. If once we perform these two, or any two combination of transformations, what the result would look like. And in this case, it's the simplest one. You do it one at a time, but the result is no different. But if it doesn't different by multiplying the size by 6 at the same time. And so you can see, you can imagine and describe verbally that, oh, the result is simply the relation by a factor of 6. This is what you get by reasoning. But that should be the result that we want. And let's hope we all agree that that's the case for this example. So that's describing bit verbally. What about metrics? Like how do we combine these two transformations using the matrix? Oh, sorry, it should be B times A. My bad. Yeah, because the thing is by the way we describe that, we multiply by 3 first, and then we multiply by 2. So if you have any vector, the first thing is you multiply that by A, and then you multiply it by B. Maybe I should stick with the I should stick with the notation we have up here. Let's get back to A times B. A times B, now I should fix that instead. So A times B mean we do the B first. Like we perform the second or the right operation first. So if you have a box and if you transform by B, that means we increase the size by 2. So now it becomes a box that has length 2. And then if we repeat that, but using the A, then we have a box that has length 6. But yeah, eventually, like the result is the relation by a factor of 6. The box is now 6 times larger. So that's the verbal. What about the matrix? The matrix is simply these two matrices combine or multiply together. And if you are patient enough, if you know some math, or if you have a tool, like you are welcome to use this tool to help you. Like for instance, let's do the two. A is 3003 and B is 2002. The result is, of course, 6006. So yeah, you can. It depends on the question, right? If I ask you to use, if I allow you to use a calculator, then please use it. If not, then you're gonna have to, show that you know how to multiply two matrices together. In this case, if you do it manually, you would have to multiply this orange row by the blue column. So it's 3 times 2 in the first entry, and then it is 0 times 0. So if you compare the formula, this is the first entry. It's the top left one. Then you get from the first row of the first matrix with the first column of the second matrix. And then we continue with the next one, which is the first row and then second column. We have 3, 0. But now we have 0 and 2. Let me write these two. Right, the rest are just, just fill in the formula. Right, but once you fill everything in correctly and do the math, then you should get the same result as the calculator that I just used. So the result, right, if you express it in terms of matrix multiplication, it is this matrix. And that's the answer for this example. If you have to explain it verbally, it is the relation by a factor of 6. If you explain it by multiplication, it is this new matrix. And that's the end of it. But the the hidden connection here is that you should also see that these two needs to be the same thing. Right? Because we do that, we perform the same transformation. We just describe it in two different ways. And if it's the same transformation, then they should give you the same result. And can you see that this matrix is indeed the relation by a factor of 6? Right? It is it. Again, if you go back to the definition, right? This relation is exactly this matrix. And so we get the result and we can confirm that they match. Right? These two operations done in this sequence gives you the relation or scaling by a factor of 6. So that's one example. Let's take a look at another example. Let me move it down here. So let's see which one I should use. Yeah, for instance, let's try rotation because that's where interesting things happen. Suppose we rotate by 45 degrees counterclockwise. And actually, like from now on, if I'm not saying which direction, you should assume that the default is counterclockwise. If you rotate that twice, what would the result be? Maybe that's a short question, and then needs some kind of explanation. So here we have a rotation by 45 degrees. So you can imagine you have a pen in your hand, you rotate the pen by 45 degrees, and you do it one more time. What would the result be? Of course, if you have to explain it verbally, then that should be the same as rotate by 90 degrees, right? It should be, right? And of course it's correct. Let me remove that. Yeah, it is the same as rotating counterclockwise to rotating by 45 degrees twice is the same as rotating by 90 degrees. Of course, that seems intuitive, isn't it? But that's the first part. If you explain this verbally, then that's the result. What about matrix? Can you compute, or can you explain what is going on here? So we have to start from this rotation first. So rotation by 45 degrees, it can be, let's say it's A. And if you go to the formula we have up there, like it's cosine 45 degrees minus phi 45 degrees, sine 45 degrees, and cosine 45 degrees. This is the matrix that you need to multiply to a vector if you want to rotate anything by that amount of degrees. And if you do the math, then you should get square root of 2 over 2 minus square root of 2 over 2, square root of 2 over 2, and square root of 2 over 2. Okay, lots of numbers, but still simple enough. Then what we are doing here is we multiply A by itself. If you have any vector, you apply it twice, then it's the same as multiply A by itself. Before we can apply that. Before we do the math, let's see what we have on the left hand and on the right hand side. Right, on the left hand side we have two matrices, right? And then on the right hand side, right, it's a result. And we just make a note that the result should be rotation by 90 degrees. And the result should be the rotation by 90 degrees. And if it's a rotation by 90 degrees, then it should be what? It should be this matrix. And again, I'm plugging in numbers yet. Right? But if it is the rotation by 90 degrees, then in this, it should look like that matrix. Right? Because by definition, this is exactly the rotation by 90 degrees. So that means if we multiply A to itself correctly, the result should be this matrix. And you can see that this matrix is easier to compute. We don't have to do, all this math. And because if you do the math here, then this matrix should give you 0, -1, 1, 0. And you can kind of take a note, maybe make a big asterisk. Right? This matrix is a transformation by rotation, counterclockwise by 90 degrees. Which looks simple, isn't it? Doesn't it? Like 0, -1, 1, 0. So okay, so if we understand everything correctly, the result after the multiplication should be this matrix. Then of course, let's try that. Right, and there are two ways. If you are allowed to use a 2, then of course please use a 2. Like here we can put it to be square root of 2 over 2. That's A, that's A, that's A, that's A, or should be minus. Okay, so that's an A. And let's remove the B. What we need is a multiply to itself. And let's see what the result is. It looks similar, isn't it? I mean, they look the same. It is what we expect, right? Rotating 45 degrees twice should be the same as rotating by 90 degrees, which is what we see on the right hand side here. Oh, and by the way, now that we are in this app, you can see this A square, and you can guess what it is. It's the same as A times itself. That's A square, and that's the same result. Alright, so yeah, it should be the same if you use calculator. But just in case, let me show you a little bit what is going on here. If you do it by hand, which is somewhat evil, I may or may not ask you to do that, but suppose you have all these numbers. And let's do it just for a single entry and see if you are correct. So to multiply that, you want the first entry, and that comes from the first row of the left matrix to the first column of the right matrix. And if you multiply them together, you can see that something interesting is happening. So in the we have this entry, square root of 2 over 2, multiplied by this entry, square root of 2 over 2, plus this entry, minus square root of 2 over 2, and this entry, square root of 2 over 2. So that's one single entry. And if you have enough time, you have to multiply everything out. Right? But can you see what the result is? We have two numbers that look similar, except one number has minus, the other doesn't have. So you don't have to do the math to see that, oh, actually they should cancel out. If you do the math, then you could, but if you do the math, then you should get 1/2 minus 1/2, which is of course 0. So yeah, it seems like we are on the right track. Like the first entry is indeed 0. We should agree with the result that we are looking for on the right. So that's the first entry. And if you repeat with the rest of the matrix, then you should get this matrix. So yeah, let's go back a step. Right? If you explain it verbally, it's just a single rotation by 90 degrees. But if you use a matrix multiplication, suppose we don't know this fact yet, then you have to multiply them together to get a matrix. That happens to be 0, minus 1, 1, and 0. So these two are the answers. Verbally, we get that. Then, if you add a matrix, we get this one. And so that's the second example of a composition of transformation. And if you see the exercises, there are more, which is of course part of the tomorrow exercises. For instance, you can dilate and then rotate. Let's think about it for a moment. What would it be if you increase the size and then you rotate that? Like what you would expect to see at the end. If you dilate and rotate, like what would be the result? If you rotate by 90 degrees and then rotate again by the same angle, 90 degrees, what would the result look like? And similar to what we just showed, like you are asked to do it both by verbally, like imagine what the result would look like, and then both mathematically using the matrix. But for the second part, you don't have to perform the calculation. Like you are free, you are welcome to use any tool you have. Just get the result out. And then see if you can kind of compare the result to the answer in the first part when we explain it verbally. So that's the transformation. That's the composition. And now we are so close. So let's talk about the extra part a little bit. So there's an extra part which is only 2 pages. Like it's kind of interesting here because we say that when we rotate twice, or we have a composition of rotations, and then we can simply add the angles together, right? If you rotate by 30 degrees and then 60 degrees, that should give you the same result as rotating by 90 degrees once. So that's what we would expect, right? But then this is what we have on what we meant by that. Right, on the right hand side, we have 2 rotation. First time by b degrees and then by a degrees. On the left hand side, right, this is the result we would expect, right? It should be the same as rotating by a plus b degrees. This two should be the same in terms of, again, verbal explanation of the transformations. But what's interesting here is that if you try to multiply the right hand side, can you guess what you would get? You get this matrix, like which seems weird. Right, there are so many terms here. You multiply cos A to cos B and then minus sin A to sin B. And you get this first entry. Then you multiply what? You multiply cos A and minus sin B to minus sin B and cos B to get the second entry, and so on. But at the end, the thing we get from this multiplication is that the left hand side, which is the cosine of the sum of angles, right, can now be expressed in terms of sine and cosine of those 2 angles. Also, in other words, maybe I should write it here. Right, this result of the multiplication should be the same as what we just have on the left hand side. The same as what we have, which is cosine of a plus b minus sine of a plus b, sine of a plus b, and then cosine of a plus b. So we can compare these two matrices entry by entry and see what we get. Now we get the formula for the cosine of the angle sum. Right? But back then, I'm sure it doesn't make sense to anybody, including me. Like when I first look at this formula, I say, wait, why are they, expanded in this way? But if we know this topic, and we know, it's a result of matrix multiplication, then we can see that, okay, now that you can kind of see like where these two products come from. So based on this observation, we can produce a new formulas or identities for trigonometries that you may have memorized or have seen before at some point. So that's all for the matrix composition. There are more, of course, but I intend to serve it as an introduction and to advertise that if you know this stuff, it's kind of cool. And in the future, when you need to do it yourself, you have to extend it to 3 dimensions. Then I hope this kind of serve as a nice fundamentals for those concepts. So see you next week.